Welcome to the next lecture on mobile radio propagation. Today we will start with frequency flat and frequency selective fading. We will today talk about channel models for frequency flat and frequency selective fading. Then we will look at another aspect, how fast the channel changes vis-a-vis the signal itself. So we will then talk about slow fading versus fast fading. At the end, if time permits, we will briefly have a peep at Rayleigh fading and Rician fading. Of course, as always, we will start with a brief recap of what we learnt last time. In the previous classes, we have been talking about time dispersion parameters of your fading channel. If you remember, we have a transmitter and a receiver spatially separated, and the propagation occurs through the wireless medium. So we are working in a wireless channel environment. It is possible that the transmitter and receiver are moving with respect to each other, as is the case in mobile communication. In such case, we have various time dispersion parameters to characterize the channel. We learnt last time that the power delay profile, which we can measure, is useful in obtaining the three important time dispersion parameters, namely the mean excess delay, the RMS or the root mean square delay spread, as well as the maximum excess delay. We also learnt last time about coherence bandwidth. How broad or wide is the channel bandwidth with respect to the signal makes a difference in terms of fading. We learnt last time that if two signals are separated by more than the coherence bandwidth, they fade independently. We also learnt about coherence time, which has to do with how fast the channel is changing with respect to the symbol duration. Today we will play with these parameters with respect to the signal and see what do we mean by frequency selective fading or frequency flat fading, fast fading versus slow fading. Can we have a combination of these? What does it matter? We will also look at some examples. So continuing with our notion of time dispersion parameters, we recall that they grossly quantify the multipath channel, and the three most important parameters that we will revisit are the mean excess delay, the root mean square delay spread, and the maximum excess delay. So if you recall, the mean excess delay represented by tau bar is the first moment of the power delay profile. It is given by the following formula: tau bar is equal to summation a subscript k whole squared tau k divided by summation over k a subscript k squared. Please remember, the small k represents the number of multipath channels. So if we are in a room environment where there are several multipath components, then k can range from 1 to 20 or more, whereas if we are in the outdoor environment where we do not have very many buildings or other reflectors, k can be a smaller number. There could be 6 or 8 significant reflections and hence multipaths. Now the moment we measure the power delay profile, which is p of tau, we automatically square the received strength. So a subscript k represents the channel gain for the kth path. So the equation for tau bar, which is the mean excess delay, turns out to be summation over k p tau k, which is nothing but the power delay profile, times tau k divided by summation over k p tau k. The root mean square delay spread, signified by sigma tau, characterizes the time dispersiveness of the channel. It is directly obtained from the power delay profile. it indicates delay during which the power of the received signal is above a certain value. It is the square root of the second central moment of the power delay profile. So, mathematically, sigma subscript tau is equal to under root tau squared bar, the average value, minus tau bar squared, which is the second central moment of the power delay profile. Again, tau bar squared, which is used in this equation, is nothing but summation over k, p tau k, this time tau k squared divided by summation of p tau k. Right. So, given a measured value of a power delay profile, it is easy to compute tau bar, it is easy to compute tau squared bar, and hence it is relatively easy to compute sigma subscript tau from this equation. Please recall that RMS delay spread will have a limit on how fast you can send the data bits over an unequalized channel. Okay. Today we will learn that these parameters come into play when we talk about the frequency selectiveness of a channel also. We learnt about coherence bandwidth. We defined coherence bandwidth B subscript C as the range of frequencies over which the frequency correlation is above 0.9. This is one of the two popular definitions. If we define it so, then B subscript C comes out to be 1 over 50 sigma subscript tau. Sigma tau, if you recall, can be calculated directly from the power delay profile. The other popular definition of coherence bandwidth is the range of frequencies over which the frequency correlation is above 0.5. If we go by this definition, then B subscript C, the coherence bandwidth, is nothing but 1 over 5 sigma tau. Sigma tau is the RMS delay spread. The third notion was of coherence time. Coherence time is a statistical measure of time duration over which the channel impulse response is essentially time invariant. So, we are talking about how fast your channel is changing. Again, how fast or how slow is relative to how fast your signal duration is. If the symbol period of the baseband signal, which is approximately the reciprocal of the baseband signal bandwidth, is greater than the coherence time of the channel, then the channel will change during the transmission of the signal. We have to be careful about it. Hence, there will be distortion at the receiver. The coherence time T subscript C is defined as 1 over Fm, where Fm is the maximum Doppler shift. We learnt that the Doppler shift depends on the velocity of the mobile, the lambda or the wavelength of the frequency that we are using, and also the relative angle at which the signal impinges on the mobile. Now, we talk about the small scale fading. Now, based on the multipath time delay spreading, we can classify the multipath time delay spreading into two parts. First is the notion of flat fading. The complete expression is frequency flat fading. So, we are trying to comment something about the nature of distortion that we get vis-a-vis the frequency of transmission. So, frequency flat fading occurs when B subscript S, which denotes the bandwidth of the signal, is much smaller than B subscript C, the coherence bandwidth. This implies that sigma tau which is the RMS delay spread, is much less than Ts, the symbol duration. Now, sigma subscript tau is only a function of the environment. It has nothing to do with the signal. So, if in a small room environment with lot of reflectors, right, if sigma tau is much smaller than tau s, then in that case we will experience something called as a frequency flat fading. In these scenarios, we typically find that the received amplitude to be statistically distributed either as Rayleigh or Riccian. At the end of today's talk, we will introduce both the Rayleigh and the Riccian distributions. The spectral characteristic of the transmitted signal is preserved in the case of flat fading. The other part, based on the multipath time delay spreading, is the frequency selective fading component. This is the complement. So, in this case, B subscript s, which is the signal bandwidth, is greater than BC. Okay. Please note, it is not much greater than, just greater than starts you into the domain of frequency selective fading, but in many cases we consider Bs greater than BC. It equally implies that sigma tau should be greater than T of s, the symbol duration. In this case, inter-symbol interference occurs. So, please note, we are trying to distinguish the effects caused by flat fading channel and frequency selective fading channel. Again, both these are coming from the time dispersiveness of the channel, that is multipath time delay spreading. For the same signal that we are sending, if the time delay spread increases, okay, in that case the channel will tend to become more frequency selective. The other features of a frequency selective channel is that the spectral characteristics of the transmitted signal is not preserved. This is a major impediment. But it can be also viewed from the other side of the coin, which is you can have uncorrelated fading for one part of the signal with respect to the other part of the bandwidth. So, in a frequency selective scenario, I can have inherent ways and means to overcome or reduce the effects of fading. The good part is if your Bs, which is the bandwidth of the signal, is much greater than Bc, you tend to resolve the multipath components. This we have seen in the case of ultra wideband UWB communication, where each multipath is resolved. Clearly, UWB falls into the second category, which is frequency selective fading. Okay. Usually, it is unfair to comment without the knowledge of both the signal duration and the delay spread, whether the channel is frequency flat or frequency selective. However, in the case of UWB communication, even if you go into the room environment, you tend to encounter frequency selective fading because of the large bandwidth for ultra wideband scenario. Graphically, let us look what is happening. In the first case, which is the flat fading scenario, on the x axis we have plotted the frequency. Here you can see that the signal bandwidth is represented at the base band in green and the coherence bandwidth in orange, and you can see that the coherence bandwidth is much larger than the signal bandwidth. If such a situation occurs, you encounter flat fading. In such a situation, you will also find that the received signal is not distorted. Whereas, on the frequency selective situation, the signal is clearly, the bandwidth of the signal is larger than that of the coherence bandwidth. I do expect that my received signal will be distorted when I look at it from the frequency domain perspective. Question?
In frequency flat fading, we don't expect the signal to be distorted. And therefore, what's the best way to restore the signal if it goes into a fade?
Question being asked is, in the scenario of flat fading, the entire signal bandwidth is faded identically. There is a correlated fading going on here for the signal. So, if the signal fade, it fades. You cannot say that a part of the signal will undergo fading and the other part will not undergo fading, or you cannot have a mitigating effect for fading. So, how do we resolve or overcome the problem of fading? For that, clearly we have to resolve to other measures. We go for the next dimension, which is the time dimension. If my channel is slowly fading or fast fading, I can transmit copies of the same signal at different time durations separated by more than the coherence time, so that they will undergo independent fading. Or maybe I can use multiple antennas and use some kind of a spatial diversity, so that I can overcome the effects of frequency fading. Okay. Clearly, frequency diversity will not work in this case. We will talk at length about these two dimensions. One is the frequency dimension and one is the time dimension as we go along in today's talk. And we can have a mix and match of a frequency selective channel or a frequency flat channel, a slowly varying channel or a fast fading channel. Fine. So, let us talk a little bit more about this flat fading thing. Flat fading occurs due to fluctuations in the gain of the multipath channel, which leads to the change in the amplitude of the received signal with time. A good example is Rayleigh fading. If you do have a line of sight also, you tend to get Riccian fading. Flat fading occurs when the symbol period of the transmitted signal is much larger than the delay spread of the channel. Clearly, these effects start vanishing if your multipath component reduces. For example, if we use a very directional, a highly directional antenna, both at the transmitter and receiver, we wipe out most of the multipath components. In those cases, your delay spread of the channel starts going down. Just by the selection of the half power beam of the antenna can affect your delay spread, and hence whether the channel is flat fading or frequency selective fading. So, when you design a communication system, all these things will come into the picture. The bandwidth of the applied signal is narrow as compared to the coherence bandwidth of the channel. We are talking about the flat fading scenario. Flat fading may cause deep fades, out of which we have to only come out using some other technique like using time diversity or antenna diversity. The other way to come out of these deep fades is to increase your transmitted power. This is a poor solution because usually we do not want to solve the problem of fading by increasing the transmit power. There are other smart techniques to overcome the effects of fading without resolving to the increase in the transmit power. However, it still remains one of the possibilities. Let us now look at certain flat fading channel characteristics. Assume that S of t is a signal being sent. It passes through a frequency flat fading channel described by h of t comma tau, and the received signal is r of t. Okay. So, if you want to represent S of t in the time domain, it may look like a pulse. Now, for a flat fading channel, clearly we do not have multiple pulses coming out. The h of t is a single impulse. On the other hand, if we were talking about frequency selective channel, the h of t would be either spread or you will have several pulses here, right. So, it is a simple way to explain whether the channel impulse response is frequency flat or frequency selective. Now, clearly what you receive here is a convolution of s of t with h of t comma tau, and you get a slightly spread pulse like this. Let us see what happens in the frequency domain. So, let us say the approximate frequency domain representation of s of t, s of f is given by this, is just a representation. It may not be the exact Fourier transform. An exact Fourier transform would be a sinc pulse here. H of t in the frequency domain h of f probably can be represented like this. What is important is that h of f is much larger than s of f. So, Bs, the bandwidth of the signal, is smaller than the bandwidth, the coherence bandwidth of the channel approximately. So, what we get is a product of these two here, and as expected there is hardly any distortion. This is exactly what happens when we work in a flat fading scenario. However, suppose I would like to decrease my signal symbol duration. I can do that. Today we are pressing for faster and faster data transmission, which forces us to reduce Ts. In that case, we will have a much broader h of t comma tau, maybe multiple impulses here, and then you will see that the situation changes. We will talk about it. Now, suppose we have to generate or synthesize a flat fading channel. We can do so either in software or hardware using something like this. Here we are trying to explain how to generate the Rayleigh fading signal. So, Rayleigh fading signal, if you look at the PDF, it can be obtained by square root of the squares of the two Gaussian random variables added in quadrature. So, this is exact depiction of that. So, we have a Gaussian noise source and another independent Gaussian noise source here. Right. Here we have a shaping filter, a balanced modulator with a 90-degree phase shift, so cosine and sine, and then multiply. This is nothing but your Rayleigh faded signal. The other part is the frequency selective channel. Let us now talk about it. Frequency selective fading occurs when the channel multipath delay spread is greater than the symbol period. The same channel will behave as a frequency selective channel if my Ts, the symbol duration, goes down. Symbols clearly face time dispersion. The channel will introduce intersymbol interference because now I have a delayed response of several impulses being represented by the h of t. The bandwidth of the signal s of t is wider than the channel impulse response h of f, which will be the transfer function. This frequency selective fading causes distortion of the received baseband signal. If we look at it in the frequency domain, it will become much clearer. So, let us look at the frequency selective fading. Again, we have a frequency selective channel represented by h t comma tau. The signal that we are sending is s of t, and what we receive is r of t. Now, in this case, we have in the time domain, please note, S of t much smaller in terms of the width of the symbol T of S. Here, for the sake of simplicity, we have drawn a continuum, but in most cases you will have lots of peaks and troughs, as we have seen in most of the power delay profile measurements. What we receive here is a convolution of S of t with h of t comma tau to get R of t, which will be a distorted form. This is clearer in the frequency domain. So, let us say S of f represents the frequency domain representation of S of t. H of f can be given like this, and if we multiply S of f with H of f, we get a much distorted version of S of f. Clearly, the frequency selective fading has introduced distortions, and hence the name frequency selective fading is justified. It selectively fades some of the frequency components and lets go of others. If we were to draw the frequency selective fading channel model, it can be represented by a tapped delay line. By far, this is the most popular model for a frequency selective channel. Here we have an input signal, say x of t. Now, we can have either a direct path or several multipaths. So, this channel model is almost intuitive. What happens for the various multipaths? We introduce a delay term, which will be resulted by a phase shift and a amplitude multiplicative factor. So, we take this first version and multiply it with R0 t e raised by j phi t. Then this corresponds to the second multipath, so and so forth up to L multipaths. This is represented by a tap delay line model. Then we add them up, because that is what we get at the receiver, and we get the faded signal output. If we have to generate in the lab scenario or by simulation frequency selective fading, then we can deploy this kind of a setup. Now, the question is, what is flat frequency, flat fading or frequency selective fading? What are the common rules of thumb? How big is big? Clearly, by saying Ts much greater than sigma tau does not give us any definitive answers. Okay? Remember, we defined flat fading when Ts, the symbol duration, is much larger than sigma tau, the RMS delay spread. How large? So, a rule of thumb is an order of magnitude. So, if T of S is greater than or equal to 10 times sigma tau is the RMS delay spread, then we say that the channel is behaving as if it is flat fading. On the other hand, if T of S is less than 10 times sigma tau, you can say that the channel is frequency selective. Sigma tau has nothing to do with the signal. So, the same channel, the same room can behave either as a flat fading channel or as a frequency selective channel, depending upon what my symbol duration is. Fine? Question?
So, what about the situations in the intermediate situations?
Okay, the question being asked is, what happens to the case when Ts is less than 10 sigma t or greater than this one? Is that the question? So, clearly these two cases should cover all the scenarios. If you are in between, maybe Ts is approximately equal to sigma t, right? Then what do you do? So, those are clearly the gray regions where your signal will behave somewhere in the middle. So, distortions will start coming in, but though not significantly. Okay? Here you are absolutely safe. No matter what happens, there is absolutely no distortion. in this case there will be distortion and you can confidently overcome the effects of fading. There is no way out that you cannot overcome fading by using frequency diversity. Somewhere in the middle your frequency diversity technique will not work effectively, you will still have some deep fades and you will have signal distorted. So those are the cases when Ts is approximately of the order of sigma tau. Okay. Let us look at an example. Let us consider a multipath channel where by measurement the power delay profile looks like this. There are 3 impulses received, one clearly coming from the line of sight and 2 from reflections. Now for this, if you calculate tau bar, it comes out to be 1.26 microseconds. The tau squared bar comes out to be 3.79 microseconds squared. These are using the formulae discussed before, and the root mean square delay spread sigma tau is 1.48 microsecond for this channel. Now the question is, what is the case when you will experience flat fading or when will you experience frequency selective fading? So using the rule of thumb, Ts greater than 10 sigma t, which is greater than 14.8 microsecond, will lead us to flat fading scenarios, whereas for much less than this one you will have frequency selective scenarios. Question?
Sir, we have a Nyquist criteria which has a interruptible frequency selective fading means which it has interruptible interference, and there is a particular Nyquist criteria which specifies when interruptible interference occurs. So why do we have a rule of thumb?
Okay. So the question being asked is, for intersymbol interference we can overcome the effect by using something called as a Nyquist criterion, right, where I can overcome the effects of intersymbol interference. It does not say that intersymbol interference will not occur, but we can sample the signal in such a manner that at the sampling instances only the effects of the other symbols are almost zero. The same is the case here. ISI or intersymbol interference will occur, but we have to resort to some kind of pulse shaping which will be required to satisfy the Nyquist criteria, and then when we sample it, yes, we will overcome the effects of ISI. But in frequency selective channel, symbols will run over the subsequent symbols, there will be interaction between the symbols. So pulse shaping is required to overcome the effect. Similarly, equalization can be done to undo the effects of the spreading.
So Nyquist criteria is related to how much sampling time and how much sampling interval should be there to overcome the fading.
Yes.
Overcome the intersymbol interference, but intersymbol interference will occur.
Yes. So the question being asked is, does intersymbol interference always occur? How Nyquist criteria can help it overcome? The answer is, for this given channel, intersymbol interference is a part of life. You will get ISI. The question is, ISI can hamper your performance. It can limit your data rate. It can distort or break down your subsequent symbol with respect to others. However, if we want to satisfy the Nyquist criteria, which is the pulse shaped design, right, then if we sample at the correct instances, the effect of the subsequent symbols will not be seen. That has nothing to do with the channel. The channel will introduce intersymbol interference. So while designing many wireless communication systems, the first thing is to understand the channel model. Then you have to understand the effects, for example, for multipath spread, you have to understand the intersymbol interference, and then accordingly design. This sigma t will tell you till how many symbols your ISI will last, and that will help you to design a pulse shape which will help you overcome. So, those are the inputs we can take from the channel. Otherwise, the Nyquist criteria has to be satisfied independently. Now, let us look at the types of small scale fading. These are clearly based on the Doppler spread. Doppler spread, we know, comes from the relative motion of the transmitter and receiver, or even if the transmitter and receiver are fixed, the channel might be changing. So, again we can classify the types of small scale fading based on Doppler spread into two parts. One is the fast fading scenario. Here there is high Doppler spread and it occurs when T of C is much less than T of S. T of C is the coherence time of the channel, T of S is the symbol duration. The channel variations are faster than the baseband signal variations. If this occurs, we say that it is a fast fading scenario. The counterpart is a slow fading scenario where we have low Doppler spread. The relative motion of the transmitter with respect to the receiver is much slower than how fast the signal is changing. Here we have the TC, the coherence time much greater than the symbol duration T of S. The channel variations are smaller than the baseband signal variations. Fine. So, again we are talking about two types of classifications, the fast fading and the slow fading. Both of them depend upon how big or small is your T of S. Let us look at it graphically. In the frequency domain, the x axis represents frequency. In the green, we have plotted the signal, and in the red is the Doppler spread. If the Doppler spread is much larger than B of S, in that case we have fast fading. This can occur when the vehicle is moving very fast. On the other hand, if we have the other scenario where the green representing the signal bandwidth is much larger than the Doppler spread, then the motion is slow, or the transmitter and receiver are almost static and the channel is not changing very fast. In that case, we have slow fading. Clearly, this will have an implication if we are going to use time diversity to overcome fading. So, we are dependent on TC this time for our definitions, TC being the coherent bandwidth. TC less than T of S gives us fast fading, TC much greater than T of S gives us slow fading. Please note, this has nothing to do with frequency flat or frequency selective channel. We are talking about a completely different dimension. The only link, if you must try to connect these two, is the T of S. What makes them independent is that TC has nothing to do with BC. TC is the coherence time, BC is the coherence bandwidth. Fine. So, let us talk a little bit more about the fast fading scenario. Fast fading occurs due to Doppler spread. The rate of change of the channel characteristics is larger than the rate of change of the transmitted signal. As a result, the channel changes during a symbol period. So, the same symbol may undergo a different kind of fade in the start of the signal, and by the time the symbol duration is over, the fading characteristic has changed. So, inherently this kind of a symbol can overcome parts of fading. The channel changes because of the relative motion between the receiver and the baseband signaling. the coherence time Tc of the channel is smaller than the symbol period T of S of the transmitted signal. Fine. You can intuitively understand the concept of fast fading by assuming that you are moving with respect to the transmitter and you are passing through the troughs and the peaks of a fading channel. But since you are moving so fast that within the symbol interval you go from a faded point to a non-fading region. So, within the symbol duration you get in and out of fade. The fading environment changes within the duration of the symbol. This is fast fading. The other part is the slow fading scenario, where the rate of change of the channel characteristics is much smaller than the rate of change of the transmitted signal. Here the channel may be assumed to be almost static over one or several reciprocal bandwidth intervals. In frequency domain, this means that the Doppler spread of the channel is much smaller than the bandwidth of the baseband signal. Now, as was the question raised earlier with respect to what happens in between the frequency flat and the frequency selective channel, a question may be asked what happens in the scenarios where it is in between fast fading and slow fading. Well, the researchers have come out with a term called a quasi static channel, where it is somewhere in between. So, it is not a slow fading scenario or a fast fading scenario, but it is a quasi static channel. So, in that scenario you can assume that your fading is fixed over one symbol duration, but will change on the onset of the next symbol. It does not change within the symbol, but it also does not stay same for several symbols. Okay. That is a quasi static channel. So, a comment on fast fading versus slow fading. The velocity of the mobile or the velocity of the objects in the channel and the baseband signaling alone determines whether a signal undergoes fast fading or slow fading. So, if I was moving and I stop at a red light, I come into the domain of slow fading, and then when I see a green light I pick up speed and accelerate, I again get into the fast fading scenario. Now, let us try to summarize the fading classification using this two orthogonal axes. Please note, here we have put 4 components: the flat slow fading scenario, the flat fast fading scenario, frequency selective slow fading scenario, and frequency selective fast fading scenario. Since the coherence bandwidth and coherence time are orthogonal and are independent, have nothing to do with each other or influence each other, I can have a combination of flat versus slow, flat fading versus frequency selective fading, slow fading versus fast fading, and choose a combination thereof. The only link, as mentioned before, is Ts. Now, if on this axis we have Ts as also on this axis, somewhere we draw these lines. These lines on this axis is a Tc, the coherence time, and on this axis the RMS delay spread sigma tau. So, this line is the RMS delay spread. Sigma tau and Tc can vary independently, and hence I can lie here, here, here or here. Okay. Clearly, these are all fading scenarios and will require one or a combination of fading countermeasures to overcome the effects of fading. Right. So, if you are in a frequency selective environment, then frequency diversity will be useful. If you are in a fast fading environment, you have to use time diversity. Okay. If you are in a flat slow fading situation, then maybe you have to resort to increasing the transmitted power to overcome the effects of fading. It is a bad situation to be here. Now, you can flip the coin and look at the other viewpoint, which is fading classification as a function of the baseband signal in terms of its bandwidth. So, here again I have two axes, but on these axes I have the BS. BS represents the bandwidth of the signal. Again I have 4 quadrants, but the lines that we draw are BD, the maximum Doppler spread, and BC, the coherence bandwidth. Since BD and coherence time, BC and the RMS delay spread are inversely related, then we have these 4 scenarios again. So, whether you want to look at it from the frequency domain perspective or time domain perspective, you have these 4 types of combinations possible. Clearly, you can be close to these gray regions where it is somewhere in between fast and slow fading or frequency selective versus frequency flat fading. Gray regions exist. These lines are not clear demarcations. It is not a black and white scenario. Okay. Now, let us talk very briefly about fading distributions. We must talk about fading distributions at length in subsequent lectures. Statistical characterization of the variation of the envelope of the received signal over time leads us to fading distributions. The 2 most common distributions that we encounter are Rayleigh fading, which happens when we have a lot of multipath components similar to one another, but no direct line of sight. Or we can have the Rician fading, which is occurring when we have a clear line of sight as well as multipath components. If all the multipath components have approximately the same amplitude, that is, when the mobile station is far from the base stations and there are several reflectors, the envelope of the received signal is approximately Rayleigh distributed. No dominant signal component must exist. Even if there are no line of sight, 1 or 2 reflections should not be much stronger than the other reflections, otherwise you will not have Rayleigh fading. This assumption is generally true for mobile scenarios when the mobile station is far away from the base station. Whereas, as you start moving closer to the base station, you tend to have a line of sight. In that case, it will degenerate into Rician fading. If you look at the Rayleigh fading profile, on the x-axis we have the elapsed time in millisecond. Suppose a vehicle is moving along this axis, so the distance will translate it to the elapsed time. On the y-axis we have the signal level, it is in dB, so it is a logarithmic scale, hence you have well rounded profile, otherwise you will get a much more jagged received signal strength. So, the dB rounds it off. Now, this is a typical Rayleigh fading profile. If you plot and look at the histogram, you will find that it actually has the Rayleigh distribution. What is interesting to note are the presence of various deep fades. If you see, there are deep nulls here. So, this is a typical characteristic of the Rayleigh fading situation coming from multipath components. This is a measurement obtained at 900 megahertz. The scenario will change at a higher frequency. These fades will become much more frequent if we go and do the measurement at 2.4 gigahertz. when there is actually a dominant stationary signal component present, such as a line of sight or a very strong reflection, which is usually possible when the mobile station and base stations are close to each other, then the fading envelope is not Rayleigh but Rician. The Rician distribution degenerates to the Rayleigh when the dominant component fades away. So, this would be a logical place to stop. Let us summarize what we have learned today. We spent some time discussing the frequency flat versus the frequency selective fading channels. We looked at it both from the time domain as well as from the frequency domain perspective. We then discussed the channel models for frequency flat and frequency selective fading. Then we focused our attention on slow fading scenarios vis-a-vis fast fading scenarios. And then finally, we had a peep at how a Rayleigh fading looks like and what is meant by Rician fading. We will talk about the Rayleigh and the Rician distributions and more about fading in the subsequent lectures. Thank you.